Okay, hi everyone. So let's continue with our next lecture, which is the Introduction to Absorption and Design of Absorption Tower with Stages, Part 1. So in the first part of this lecture, at the end of just this lecture, you should be able to explain the mechanism behind absorption and stripping process. For the other learning outcomes, we will continue in the second and third part. So first of all, we need to know the important concepts concerning absorption and stripping. So if you can visualize the process of absorption, so this is your absorption tower. So the process of absorption is when you have a gas inlet. So this gas have some solute in it. For example, air with active SO2, sulfur dioxide, for example. So the SO2 is the solute in the gas phase. So you want to remove the solute in the gas phase by using a solvent. So your solvent here is in liquid phase. Alright, so this solvent preferably would be the solvent that can absorb the solute from the gas phase. So when the gas feed is in contact with the liquid solvent in the absorption column, then the gas leaving the absorption column, gas out, will contain less solute. Okay, ideally we want all the solute to be absorbed, but of course it's not an ideal world, so that's never happening. Then the solvent coming out from the bottom of the tower would contain the absorbed solute. So these are just what are the terms here: solvent, solute, absorption. So absorption is a unit operation where the solute transfers from a gas phase to the liquid phase. So in absorption, the solute moves from the gas phase into the liquid phase. So then stripping is just an opposite. It's just the opposite. So in stripping, the solute is in the liquid phase. So in stripping, you have liquid phase in with solute, and you want to remove the solute from the liquid phase by using a gas. So this gas will absorb the solute, and then the gas out will be with absorbed solute, and then the liquid phase coming out from the tower would be the liquid out with less solute. So this is stripping. So it's just a matter of where the solute transfer from gas phase to the liquid phase is absorption, from liquid phase to gas phase is stripping. In practice, absorbers and strippers are often used in conjunction with each other, because when you use the absorber, the solvent that you have used to absorb the solute, it can be recycled back to be used to, absorb the new stream of gas. So absorption and stripping operations can be carried out in vertical, cylindrical columns or towers containing plates or packing elements. So either you use plates or packing elements. Essentially, the purpose is to provide a surface area for the liquid and gas to come into contact, to mix with each other, and facilitate the mass transfer of the solute between the two phases. So commonly, gas and liquid streams for both operations are normally countercurrent for more effective mass transfer. So if you have a column, normally the gas would come in from the bottom, liquid will come from the top, just because gas is less dense than the liquid, and this is simpler than, and it's more effective for mass transfer. Not necessarily this is the only correct way, but this is what has been commonly practiced. And absorption and stripping columns are also much simpler than distillation, because in absorption and stripping, you don't use a condenser or a reboiler, because absorption and stripping, these are mass separating agent. We don't have any energy separating agent. So this is an example of a concurrent absorber and stripper. So the gas to be treated here contains solute in gas phase. The solvent will be in contact with the solute in the gas phase, and the solvent will absorb the solute. So the treated gas here contains less solute, and the spent solvent here is solvent plus solute that is absorbed from the gas. So we want to use back the solvent, so we have to remove the solute so that we have a clean solvent. So this solvent, spent solvent, will be treated in a stripper. So then we have another gas phase coming in to the stripper. So this gas here is a clean gas, stripping gas. Let's say, for example, steam, hot steam, for example, so that the steam, when it heats up the solvent with solute, maybe the solute is volatile and the solute will escape from the gas phase, I mean from the liquid phase, and be together with the stripping gas. So the gas here contains the solute that was originally in the gas to be treated. So then the solvent here would be the clean solvent that can be used to treat again the gas. So the job here is to separate and then absorb and separate, absorb until until it satisfies the regulatory requirements. So as we have mentioned previously, absorption and stripping can be done in either trade tower or pack tower, essentially anything as long as they can provide sufficient mass transfer between the gas and the liquid phase. So this is an example of a column, absorption column, where the gas comes in from the bottom of the column, liquid comes in from the top of the column, and the gas comes out at the top and liquid out at the bottom. So the trays here are the same type of trays like what you have heard of in the distillation design. So you can either use sieve tray, this one is what? Valve tray, or a bubble cap tray. The factors of choosing what kind of tray is the same like that in the distillation process. And you have to also consider the vapor flow and the liquid flow in the trays. Another option for absorption to facilitate mass transfer between the gas and liquid phases is to use packing instead of trays. So in a pack column, so instead of having trays, you do have the trays here. So what you have in place of the tray is the packing. So the packing here can be either random or structured packing. So in random packing, so as the name implies, so you have a section in the column where you need to put the packing. So the type of packing can be ratchet rings, pearl saddles, interlocks, and also you can have different materials like ceramic, metal, or plastics. So it depends on your fluid materials, either it's corrosive or not. So you have to take into account the choice of packing materials. And also different packings have different effectiveness, different efficiency for mass transfer. Another type of packing is structured packing instead of random packing. So in structured packing, the packing is not random, it is structured as the name implies. So different types of packing, structured packing, you can have Melapack, Flexipack, or Mons, different types. Maybe there are more type of structured packing out there. So how the structured packing is put inside the column is what you can see in this diagram. Essentially same thing, gas in from the bottom, liquid feed from the top, and then the gas out here containing less solute, and the liquid out is the spent solvent. So whatever it is, the packing, structured packing, random packing, or trade tower, the purpose, again, I just want to reiterate this, the purpose is to provide sufficient mass transfer between the gas phase and the liquid phase. So there are two types of absorption. One is physical absorption, one is chemical absorption. So as the name implies, in physical absorption, solute in the gas phase is more soluble in the liquid solvent, and therefore the solute will transfer into the liquid. Physical absorption is a reversible process where you can regenerate the solvent. However, for chemical absorption, in this case, your gas stream which contains the solute will react with the liquid solvent. So in chemical absorption, you remove the solute by having the gas solute interacts or reacts with the liquid solvent. Chemical absorption is normally more effective. It's usually preferred over physical because the equilibrium for chemical absorption is much more. I mean, this one, blah blah blah, here essentially just mean that the separation is more effective by using chemical absorption. But the drawback is you cannot reverse the absorption process. You cannot regenerate the solvent because when the solute react with the liquid solvent, then you're gonna have a different chemical altogether. It's a new species. But in physical absorption, it is reversible. You can regenerate the solvent. So physical absorption is important since it can be applied when chemical absorption is not possible, and also you can reverse the absorption such that you can use the solvent. In this class, in this course, separation processes 1, we will focus on the physical absorption instead of chemical absorption. Okay, so let's go on to our first example, dissolved oxygen concentration in water. So this is essentially a revision of your material balance knowledge using Henry's law. So let's see the question. What will be the concentration of oxygen dissolved in water in parts per million by mass, ppm by mass, at 298 K, essentially is 25 degrees Celsius, when the solution is in equilibrium with air at 1 atm total pressure? So the given the Henry's law constant is 4.38 times 10 to the power of 4 atm per mole fraction. So revise your Henry's law knowledge. If your Henry's law constant is given as 4.38 times 10 to the power of 4 with the unit atm per mole fraction, then what would be your form of Henry's law? And given also, I mean, this is what you, it's not given in the question, but you know that it's air. So air contains 21% of oxygen and 79% of nitrogen. And at 1 atm is your pressure. So Y of oxygen is 0.21. So given P is 1 atm and Y of oxygen is 21%, then the partial pressure of oxygen in air is 0.21. So instead of YO2, let's use YA, and A here is the oxygen. So Henry's law coefficient, Henry's law form that you can use is PA equals to H times XA, where H is the Henry's law constant. And then you can just replace PA with 0.21, and H is this given, and then XA. So XA here is 4.79 times 10 to the power of 6, and minus 6. So this is mole fraction. So you have to convert this mole fraction into ppm by mass. So convert into ppm mass. So ppm is part per million. So essentially it's just mass fraction expressed in parts per million. So XA is number of moles of A, i.e. oxygen, over number of moles of oxygen plus number of moles of air. Oh, not air, sorry. This is water. Okay, because X is in the liquid phase. So you know this Na is wait, sorry. Okay. 4.79 times 10 to the power of 4.7 times 10 to the power of minus 6 over 1 mole of Na plus N water. Okay, so you can convert this into mass fraction. So mass fraction is N times molecular weight, molar mass. So mass fraction would be the, let's use mass fraction as WA equal to 4.79 times 10 to the power of minus 6 times 32 for oxygen over, since the mole fraction of oxygen is very small, so you can just approximate that 1 mole of oxygen and water equals to 1 mole of water, 1 times 18. So 18 here is water, but if you don't want to do that, you can also still just try to use 0.99999 something to represent the number of moles of water. So if you do this, you shall get 8.52 times 10 to the minus 6 as the mass fraction of oxygen in water. So this is already to the 10 of minus 6, so it's already parts per million. So if you convert this into parts per million, is equal to 852 ppm. Okay, so yeah, the answer is the concentration of oxygen dissolved in water in parts per million by mass is 852 ppm. Alright, we'll continue the next learning outcomes in the next parts 2 and part 3.